so music is one of many things in nature that can be modeled by sine waves and cosine waves. And thank you, Long. I am glad you found that to be pleasing. Okay, and also expression of thanks to all of you for being here on Thursday, because I know Thursday is sort of the lecture that's not as relevant to the SAT, but more relevant to personal interest for all of you, and hopefully very helpful in school. So we found that we can transform the sine function, for example. You could also do this to the cosine function, but sine is convenient because it starts, it starts at 0 at the point t is, we're graphing this axis is t. At t equals 0, sine is 0. That's what makes sine kind of nice. That just happens to be, cosine is better really. It's just shifted, but sine is a nice one to work with. So we found yesterday that this is the amplitude, right? That what is f here? Can someone tell me? What is f? No, f is not feet. So think of what happens when, so think of the shape of sine. So f and t here are not related. So this is like f times t. This is not like ft. I'll write it in different colors. So it's the frequency. Yes, Matthew, very good. And so this determines how quickly your wave oscillates. And can anyone tell me the units of frequency?
Hertz.
Hertz. And what is hertz? What is that actually? What is the units of hertz? It's 1/seconds.
Oh, yeah.
So it's really what it is the number of cycles of a wave per second. And so there was a great physicist and engineer who invented, I think he was involved with inventing the radio. And so forget, his last name was Hertz. I forget his first name. Anyway, so yes, this is in Hertz. And what happened, you can see that the argument is always dimensionless. This thing is in degrees, which is technically dimensionful, but it's practically dimensionless. Time is measured in seconds. So when you multiply the frequency times the time, right, the seconds cancels, the units cancel. And so you indeed have a dimensionless argument. And what is this? Can anyone tell me? It's first of all the Greek letter phi, but what does it mean physically? The shift, the phase shift. Yeah, so sometimes people just call it the phase, or the phase shift, whatever. And so this determines how, moved over on time your graph is. And so the general shape of this thing is something like this. Sorry about the bad, it should be a smoother curve here. But anyway, so this is your amplitude, right? How high your function goes. Note, this is not your amplitude. It's not peak to peak. It's just from the middle axis to the peak. So amplitude, the frequency is basically a measure of this distance. It's the reciprocal actually of this distance, which is actually a measure of time. That's what the frequency is. This distance, this distance itself is actually called the period. So usually this is denoted by a capital T. Anyway, this is just jargon. There are a bunch of ways to describe the same stuff. And then lastly, if your function is shifted over by some phase, then your wave looks like that. And this is your amount of phase shift phi. Okay, so I hope this makes sense. This is just a recap of yesterday. People did fair on the quiz. Many people were confused about what the frequency was on the quiz, right? There was a question that asked you to identify the frequency. It is not 306, the frequency is not 360 degrees times the number that was here. I think it was 5 hertz. That was the right answer. The answer was not like whatever 360 times 5 is, and it wasn't it was just 5. The 360 is here to scale down your original graph, right? Because your original graph has a period of 360 degrees. So you have to get rid of that. And by multiplying by 360 in the argument, remember, the the transformations that happen within the argument go as the opposite of those transformations for the range. And so by multiplying by 360, you're effectively dividing the domain by 360, which makes your period 1, 2, 3, 4, and then your frequency will further okay. Anyway, so your frequency will define the number here will define basically the inverse of this distance, the inverse of the period. Okay, so I hope this makes sense. So those of you who take physics or chemistry, they'll talk about the nature of light. So we also discussed how light can be modeled using this thing. And we also discussed some of the properties of the functions, the cosine x and sine of x. So there's a difference between your SOHCAHTOA, this sort of middle school, early high school definition of SOHCAHTOA. There's a difference between this and your trigonometric functions. When people refer to SOHCAHTOA, they're usually referring to the first quadrant, or they're referring to these functions between 0 and 90, right? All right, I'll use x here. Again, this is just jargon, but when people refer to the trigonometric functions, they're referring to the entire thing, the entire wave, okay? So we found some of the properties of this wave yesterday. Raised more than I wanted to. So I'm going to plot both of these. I'm going to just sketch them, and let's discuss sort of how they look. So cosine looks like this, right? And sine looks like, sorry, I'm not the best at drawing graphs on this thing. Sine looks like that. Okay, so, and sine also goes this way in the negative direction. So you can see that the cosine about this axis here is symmetric, right? If you reflected, remember when we talked about, okay, Leanne, give me a sec. You asked a question, I'll get back to you. Remember when we talked about reflection? If you had, for example, generally, if you had some random shape, like, I don't know, like that, just some general curve, and then you tried to plot f of negative x, it would just be this entire thing reflected across this axis, right? So I would just, again, not the best at doing this by hand, but anyway, so it just reflects the entire thing. Well, you can see here that cosine is the exact same on the left of this of the y-axis. It's the exact same on the left as it is on the right. So you can actually just equate both cosine of x and cosine of minus x, because if you reflected this part of the graph, the right part of the graph, you would get the left part of the graph. And if you reflected the left part of the graph, you get the right part of the graph. Left and right meaning above and below the line x is 0. To the right and to the left of this line. So this is sort of the property of cosine. And we call functions in general that satisfy this property. So for example, this is not satisfying this property because the function does not equal the function of the opposite of the argument, right? F of x does not equal f of negative, right? So, see, this blue line is different from this green line. But functions that do satisfy this property, like cosine, are called even functions. Just like the numbers 2, 4, 6, 8 are even numbers, cosine is called an even function. And why it's called an even function will appear to the seniors in the month of May or June, when you're at the very end of your BC calculus class, when you learn about how to expand the trigonometric functions as series. But that's, I think, beyond the scope of what we're going to talk about. But just know that functions that satisfy this property, so cosine is an example of an even function. Generally, an even function is given by this property. When you reflect it across the y-axis, you get the same graph. Okay, and sine, you can see, is in a sense anti-symmetric, right? Because if you reflected sine across this axis, right, you would have this, and this is not, what I just drew here in the dashed line. This is not the same thing as sine of x. See, so in other words, sine of x does not equal sine of negative x. So in other words, sine is not even. But what would I do okay, so I'm gonna use a different color. What would I do to sine of negative x, which I've plotted here? So this red line is sine of negative x. What would I do to sine of negative x to make it equal sine of x? What do I need to do to this graph to make it look like this blue line, sine of x? Okay, Leon, you've asked, what about the f? Why is it not negative? So f is the function. So Leon, are you talking about this?
Yeah.
Yes. Okay, my volume is low, so I didn't really hear you, but why is the function not negative? So the function is not negative. The function eats up an argument. It's the argument. So it's the thing that's in parentheses that's negative. Okay. I don't know if I'm answering your question. The function is not. Okay, but actually your comment is very relevant here, because what do I need to do to this red line to make it equal to blue line? Well, I need to take the opposite, right? If I now reflected, so this is one, so from sine of x was in blue, right? And now I've written sine of negative x, which is in red. So that's the first transformation. Now if I make a second transformation still, if I take the if I negate the entire function, right? So I take negative sine of negative x. So now I'm flipping this negative sign, it flips vertically. Remember from our talk about graphing? And if I flip this vertically, this point becomes this point becomes this point becomes this point. In other words, you have the green, you're back to the blue line. So evidently, sine of x does not equal sine of negative x. So in other words, sine is not even, but sine of x does equal negative sine of negative x. And functions in general that satisfy this property, so I'll summarize, sine is that. And functions that satisfy this property are called odd, as you might guess. So this is the general form of functions that are odd. And again, the seniors who are taking calculus will see that, see why these things are called odd and even in the very end of your calculus course, which is, I think, the most exciting part of all of high school math. Okay, so does anyone have any questions about what is an even function, what is an odd function? So let me ask you a question. If I graphed our old friend, the parabola, that wasn't a good drawing. Ah, that was even worse. Okay, y equals x squared. Is this even or odd? Even, because if I were to reflect the right hand side onto the left hand side, I would get the same thing, right? So in other words, there are many ways you can write this, but if I were to take the negative of the argument, right? This is what this means right here. When I wrote f of x equals negative equals this line right here. This is satisfied by y equals x squared. Because if I take y negative x squared, well, negative x squared is just the same thing as x squared, and I'm back. So you can see that this is even. On the other hand, what about something like y is x cubed, let's say. So x cubed looks like this. So if I reflected this across the x-axis only, if I reflected this across the y-axis only, I would not get the same thing. I would not get x cubed. No, so Aditya, if you were just talking about x cubed, I'm not sure if you were talking about x squared or x cubed, but x cubed does not equal negative x cubed. Negative x cubed looks like this, and this is not the same graph. But what do I do to this blue line, this blue graph, to make it equal to green graph? Well, I take the negative of it, right? I put a negative sign out front. And this will take me back to the green graph. So x cubed is odd. And so generally polynomials that have an even degree are even, and polynomials that have an odd degree are odd. So now you're starting to see the meaning of these words. But as to why, as to why sine and cosine are called even and odd, that is something you'll encounter later. Okay, so so anyone have any questions? I should have asked a long time ago about this. No questions. Okay. So this is very powerful. And we discussed yesterday that even messy waves, in a sense, can be written as the sum of sine and cosine. I plucked that guitar string and you saw that its waveform was like, something like that. And so it had some general period, but there was sort of stuff in between, right? And we modeled this using some graphing program. And this is actually a fantastic result that is way beyond the scope of the SAT, but okay, Nishan can't see the screen. Can everyone else see the screen?
Yes.
Okay, Nishan, I'm not sure what. Okay, hopefully it'll resolve itself. Okay, but anyway, this is a result called Fourier's theorem. And again, way beyond the scope of the SAT. But I want you to be familiar with some of these words. Fourier's theorem, that you can express a wave, any general wave, no matter how complicated, as the sum of sine and cosine waves. And maybe if you study some of this in college, you'll encounter this in your second or third year. Okay. Today, the real goal of today is to prove a few important identities. And I think things that you have used before. Okay, so I don't want to leave people behind. Nishan's screen, it says it's loading. Yeah, Nishan, try logging out and logging back in. Yeah, thanks, Leanne. Okay, so, and as always, this is being recorded, so you can always go back and listen. Okay, so I think everyone knows what the Pythagorean theorem is, for example. It's the most important theorem in geometry and trigonometry, and you've used this probably since 5th or 6th grade. So if you have a right triangle, the Pythagorean theorem says, as everyone knows, that a squared plus b squared is c squared. But has anyone ever proved this before to you? I would doubt that you've seen a proof. Maybe some of the juniors and seniors have seen a proof.
They probably did, but we probably yourself forgot.
I actually don't know if, so there's actually, there are a few books that have been written that have compiled all the different proofs of the Pythagorean theorem because it's it appears everywhere in nature and there's so many ways to prove it. And the proof I'm going to show, so first of all, none of the proofs are, I mean, the one I'm going to show you is pretty straightforward. It doesn't involve much math. It's more geometric. Anyway, so I hope everyone pays attention to this because this is something you can show your friends and stuff. It's really the proof I want to show you is a very elegant proof of the Pythagorean theorem. So we know where we're headed. We know that a squared plus b squared is c squared, and this is what we're trying to show, right? So I'm going to start with some right triangle. I forgot to denote that it's a right triangle with legs a and b, and we want to find what this is, right? And the way you do a proof is you have to be hard on yourself. You have to assume that you don't know what this is, right? And the rigor of the proof will lead you to what it is. So we're trying to find this leg, and we don't know what it is. Okay, so I'm going to draw a square, as you can see here. I've drawn this square, and I'm going to split it up into such a way that contains 4 of these triangles here, and there's going to be some area of this square that is remaining. And the way I'm going to split it up is in a clever way. I'm going to put this triangle in the bottom left corner, and I'm also going to put it in the top. I'm going to rotate it, and I'm going to put it in the top right corner. Okay, and so here it is in the bottom left corner. Does everyone see it? There. Okay. That's the first triangle. And I'm also going to put it up here. Okay, so it's extending a little bit beyond the figure, but I think that's not really good. Sorry, I want this to be at least looking good. Okay, there we go. That's much better. Okay, so if I connect these lines, so first of all, the two triangles I've drawn are the same triangle. I've just, if you look at it, I've just rotated it. I flipped it. It might, okay, this drawing really is not good. Okay, that's a bit better. So first of all, these triangles are congruent, right? They have the same exact shape. They're just rotated. And so now I'm going to draw few more lines here, and that will show you that now I have 4 congruent triangles inside this square. Does everyone see the 4 triangles? Here's triangle 1, triangle 2, triangle 3, triangle 4. And they're all congruent. So they all have the same area and they all have the same dimensions. Okay, so this is, and now I'm going to label the legs. So I'll do this in another color so it's clear. Here's A, this is A, this is A, right? And this is also A, and this is also A. And now B, I'll put in green. So this is B, and this here is B. Okay, so does everyone agree so far that I've divided the square into four triangles, and now I have 2 remaining squares? Does everyone see the 2 remaining squares? Can someone tell me what the dimensions of this square here are? First of all, it's a square, so its sides have to be the same, right? So this green square, what are its dimensions? Someone messaged in the chat. It's B by, yes, it's B and B, and yes, lowercase, yeah, I know what you mean. You probably know. So this is B and B, right? Because this is B, so this has to be B, right? And this here was B, so this has to be B. So what's the area of this square? What's the area of the square? It's just the side squared. And what's the side? It's B, so the area of this squared is B squared. And now what about this smaller square? That doesn't really look like a square, but it is a square. I'll write it in blue. What about this one?
A squared.
Yes, A squared. And why? It's because this here is A, which means that this is A, which means this is A. So this is A squared. Good. So apparently, when I divide this square up in this way that has 4 triangles, 4 of these little triangles, occupying some of the square's area, that the remaining area is A squared plus B squared. Okay, now I'm going to do the same thing. I'm going to draw these 4 triangles in such a way. So I'm going to occupy this new square on the right using the same 4 triangles, but I'm going to distribute them differently. And this time I'm going to distribute them all along the corners. So here I had 2 in the corners and then 2 sandwiched, these 2 sandwiched in between. So now this time I'm going to put them all in the corners. And the way I'm going to do this, I'm going to put one of them here. Okay, that's a bit too big. One of them will, okay. Forgive my artwork. That was really pathetic. Sorry, people. Okay, I think you get what I mean, right? Okay, there's one triangle. And now here's another one. And here's another one. These shouldn't overlap. They're really actually tangent to each other. And then here's the last one. Okay, so now you can see same 4 triangles, right? And we know, the sum of, okay, I'll number them just as I did in the last example. So triangle 1, triangle 2, triangle 3, triangle 4. And so because they're the same 4 triangles and because all these triangles are congruent, the sum of 1, 2, 3, and 4 is equal to the sum of 1, 2, and 3, and 4 here, right? So this thing here, whatever is left here, oh my gosh, that was bad. What must its area be? It really is a square, even though it doesn't look like it in my drawing. Well, its area, I hope, okay, Nishan is back. So the area of this inside square is the same. It's the remainder of the area of the entire square when you subtract out 4 of these triangles. And what is that remainder? That remainder is A squared plus B squared. So we know that this thing is A squared plus B squared. But we also know that this thing itself is a square, right? And we know that this right triangle here did not come out good. But we know that this is B, labeling the legs again. I'll use the colors. So B, 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 and A. So if we call this last leg C, right? So here's C, this is C, the hypotenuse is C, then what is the area of this square if the side is C? This is sort of the punchline. Someone say it. C squared, yes. And so here is the proof of the Pythagorean theorem. So we basically, in summary, we had two squares, right? And we split them up two different ways using the same four triangles. And in one way we split it up, we found that the remaining area was b squared plus a squared. And the other way we split it up, we found that the remaining area was c squared. And because the areas are the same, a squared plus b squared has to equal c squared. And that is the Pythagorean theorem, that these things are equal. So I hope this was an elegant proof. It's not very computational. There are some very computational proofs of the Pythagorean theorem, but this is very much, like you could explain this to, I feel, to a 5th or 6th grader and they would understand. Okay, so any questions about this? Does this make sense?
Yes, it makes sense.
Great, thanks. Okay, good. So we've shown that a squared plus b squared is c squared. And now I'm going to derive a very famous trigonometric identity using this. And to do this, I'm going to take a unit triangle. What I mean by unit triangle is that the hypotenuse is 1. In other words, C is 1. Okay. And I'm going to express the legs in terms of this angle here, theta. The screen is, okay, there we go. So first of all, can someone tell me what is sine of theta here using this triangle? Anyone?
A.
Sine of theta is actually A, and if you were very good, if you were to show sort of your work in a sense, sine of theta is opposite over hypotenuse, and opposite over hypotenuse is A over C, but C is 1, so this is A over 1, and A over 1 is A. Similarly, what is cosine theta? Anyone?
B.
B, and yes, the reason is that it's adjacent over hypotenuse, which is B over C, not A, B over C. And this is, C is 1 again, so this is B over 1, and this is B. Okay, so sine of theta is A, and cosine of theta is B. So now I'm going to put this. Okay, so okay, so now I'm going to put this fact into here. And I'm going to put this fact into here. So in other words, I'm going to substitute what I found into the Pythagorean theorem. So a squared plus b squared is c squared. So a is sine of theta. So a squared is the sine of theta squared. And similarly, b squared is the cosine of theta squared, right? Just squaring both sides. And supposedly, when I add this all together, I got c squared. But c squared is 1. You know, it's 1 squared, which is 1. So my final statement is that the sine of theta squared plus the cosine of theta squared is 1. And usually, because people don't like writing parentheses, there's a more convenient notation for this when writing the sine of, sine theta squared and cosine theta squared. Instead of writing sine of theta squared, people write sine squared theta. And this means the same exact thing. So the squared becomes sort of next to the sine. So this is a notation, and it denotes that so these are equivalent. Okay.
So wouldn't it change the beta squared?
Beta squared.
Because you would distribute the parentheses or the 2 in the parentheses.
You distribute the 2. I'm not sure what you're referring to. You would not. There's nothing to be distributed here.
Because it's in parentheses.
Oh, I see. Okay. Well, shouldn't it affect? No, it should not affect the theta. So remember again, sine of theta is not a number. So sorry, sine is not a number by itself. So sine is not like a number like 5, 6, 7, 13, whatever. Sine is a function. So if sine were a number, so say sine were 5, which it is not, then you're absolutely right. You know, if you were to take 5 theta squared, yes, you would have 5 squared theta squared. But sine is not a number, right? We talked about how sine is a function. Sine eats numbers, and it's a machine, right? Same with cosine. You give it a number theta, and it spits out a dimensionless number between -1 and 1. That's what sine does. So sine, you can think of it as a function, f of theta. And when you square a function, you don't square the argument. You just square the function. And generally, people write a function squared as something like this. So you have to realize that theta is not in a multiplicative relationship with the function. This is a notation. So this is something you have to wrap your mind around. That when I write sine of theta, sine itself is not a number. So I hope that makes sense. I tried to emphasize this the other day, but I know it takes some getting used to, especially if you're new to this all. So does that make sense? Does that answer your question?
Yeah.
Okay. That is a good question. Okay, so apparently sine squared of theta plus cosine squared theta is 1. And I would like to demonstrate this to you using a graph. And so I'm going to go to my screen. Okay, so you all should be able to see this. How do I do this? Okay, here. So you can all see this graph, right?
Yeah.
Okay, so here's cosine, right? And here's sine in blue. Okay, so now can someone tell me, we haven't talked about what would happen if you square a function, but we have talked about what happens if you do, if you take the absolute value of a function. And when you take an absolute value of a function, basically all the negative y values become positive y values. So the absolute value would have, I can't draw on this unfortunately, but the absolute value, would reflect. Can you see my cursor if I do this? The absolute value.
Yes.
Right? So the square is kind of like the absolute value, not exactly though, because it changes your actual values. But it has the similar property of reflecting, not reflecting, but it turns negative numbers into positive numbers. So we would expect that sine squared, in fact, here's a good way I can do this. I can draw on it this way. So sine squared, so here's my sine graph, right? So sine squared, we would expect to look, it should all be positive, right? And it'll end up looking, it'll have the same peaks, right? But all this negative stuff will become positive, right? So sine squared might look something like that. And cosine squared, same thing will happen to cosine. Here's the peak, here's a value.
Wait, so,
Go ahead.
so what happens to the negative of the blue and the red?
Oh, like on this side of the graph?
Yes.
Yeah, so the same thing. So I'll draw it. So that's what happens for cosine, right? So it's the same thing that happens on the right side. Sorry, my graphs aren't too good. And what I can do for sine is, yeah, and so sine will look the same way. So this is just an intuitive sort of understanding what happens to cosine squared and sine squared. I'll graph it in the actual grapher. So you can see that basically it's as if the functions got squished a bit and moved all into the positive y areas. Okay, so let me plot. So here was cosine. Here's cosine squared, and that looks pretty close to what I drew. Okay, and here was sine squared. Sine, sine. The blue function is sine, and now here is sine squared in purple. So that looks pretty close to what I drew. So this fits our intuition of what happens when you square a function, right? You have all positive values, and they all. Okay, so apparently, if our thing is correct, if this statement here is correct, that sine squared plus cosine squared is 1. What should happen if I plot sine squared plus cosine squared? What should I get geometrically? Y equals 1. Very good. I should get Aditya's right. I should get a line basically. So if I were to plot this, I should just get a line that goes just like that. And indeed, here is that last plot. It's plotted in black. And so you can tell, here it is, this line, right? So it's pretty amazing to me that these functions, sine squared and cosine squared, which in a sense model change, right? They model, they're a, what is sine squared and cosine squared? It's basically the square of functions that are derived from motion along a circle, and motion along a circle is the most changing, right? You're constantly accelerating in the direction of the circle. It's the most, it's sort of the function derived on the most movement possible. Uniform circular motion, you're constantly accelerating. And yet when you square these functions and you add them together, you got this beautiful constant line. Okay, Leanne has a question. Go ahead, Leanne.
The black one, the black color, this is cosine squared x plus sin, or sin squared x. How come it's not like squared, like a U kind of shape, or like a line that goes like diagonal?
Okay, I'm not sure I'm understanding.
Like why is it like straight?
Oh, why is this line like the black line?
Yeah, straight. Since it has like a square.
Oh, but it is so sine squared and cosine squared is equal to 1, and so this black line is just 1. Look, if I were to graph y equals 1, I get the same line. See, I graphed y equals 1 in red. It's the same exact line. Does that make sense? It's. I think you're confusing things. Okay, so I added 2 things squared and I got 1, and this is basically a plot of the number 1. So if I were to remove these graphs, this is just y equals 1, which is a constant function.
What if x equals that, and like you change the variable? Is that possible?
What if x equals that, and can you? I'm not sure.
Like, what if x equals y? Like instead of the x, you put the y.
So x here is the domain. X here is not what you're. So x is on this axis. It's on the horizontal axis. So it doesn't make sense to change. Doesn't make sense to change x and y. I'm not sure I'm following what you're asking. Okay, Leanne, can you stick around just after the lecture for a bit if you.
Okay.
Yeah, I want to make sure I'm clarifying your question. But anyway, this is the main result, and I graphically showed you that it's also true. That's all I really wanted to say. Okay, so you will use this identity thousands of times in calculus and beyond, and there are some other properties that can be found using this property. Mainly if you divide this entire thing by, say, sine squared. So I'm going to take my original sine squared plus cosine squared is 1, and I'm going to divide through, which is fair in algebra, right? You can divide through by, say, sine squared. And so this is not really any different from this. I'm just manipulating it a bit. Well, sine squared divided by sine squared, sine squared of theta divided by sine squared of theta, that's just 1, just because any number divided by itself is 1. And cosine squared divided by sine squared. Well, this is, remember that tangent is sine squared over, tangent is sine of theta divided by cosine theta. It turns out that there's another function called cotangent, which is just 1 divided by tangent. So it's just a notation, cotangent. So this thing, cosine squared divided by sine squared, is cotangent squared of theta. And 1 over sine squared, well, 1 over sine, there's a function called secant, which is defined as 1 over sine. Sorry, what's called cosecant. That's 1 over sine squared, 1 over sine of theta. So 1 over sine squared of theta is cosecant squared of theta. And so this might look like alien gibberish to you, but for the seniors who are taking calculus, you'll be writing this 100 times or more, I don't know. Especially when you're doing integrals, okay? And similarly, if you divided through by cosine, right? So now I'm dividing by cosine squared. You would get an analogous statement. So sine squared divided by cosine squared, well, that's just tangent squared. Cosine divided by cosine, that's 1. And 1 over cosine squared is called secant squared, because 1 over cosine is secant. So anyway, so this is just something for the seniors if you, okay, you use this, Matthew said he used this a ton of times in pre-calc. Good. So I'm glad this is review. Honestly, I don't even memorize these things. I just write this. I was talking to Patricia about this a few days ago. We were both like, yeah, we just, anytime in high school when we needed these things, even in college, I don't remember these things. I just derive them based on this. So this is the thing to remember. Sine squared plus cosine squared is 1. Okay, lastly, I would like to derive what is called the double angle property. So we found that sine squared plus cosine squared is 1, which is great. But what is, like, say, sine of the sum of 2 angles? This does not equal. Sine is not a linear function, and therefore linearity is not preserved, right? This is the statement of linearity, and this is not true. The sine of a plus b is not the sine of a plus the sine of b. As tempting as it would be to write this. So what is the sine of a? So here I'm using Greek letters, alpha and beta. Okay, what is the sine of alpha plus beta? And it's actually not hard to figure out what this is. And I have a feeling that most of the juniors, if you've gone through pre-calculus, you will have seen this, but I'm going to just show you what it is very quickly. Can someone tell me, using our knowledge of trigonometry, so I'm going to give you that OP is 1, just so that this thing, so this distance here, this is 1, to simplify things, okay? So can someone tell me what PQ is? Look, here's PQ. Using your trigonometry knowledge, what is PQ? Given that this is 1. Well, it turns out that the sine of beta, sine of beta is opposite over the hypotenuse. So sine of beta is PQ over 1, which is PQ. So sine of beta is PQ is sine of beta. And similarly, OQ is the cosine of beta, right? Because if you took the cosine of beta, you'd have OQ over 1, right? Adjacent over hypotenuse. And so OQ is just cosine of beta. Okay, now what is AQ? Can someone tell me what AQ is? Look, it's the same thing. It's just the sine of alpha, because this is also 1. And PR, where is that? PR. You see how this angle is also alpha? You can use a little trigonometry to show that. What ends up happening is this angle is alpha. Anyway, so PR, we're running out of time, so I'm kind of going fast, but PR is the cosine of alpha. Sorry, let's see. AQ. Sorry, AQ is AQ. Okay, I actually don't know if OQ is 1. So I'm gonna write AQ is let's see, so sine of alpha would be AQ over OQ, just to be sure. And PR is cosine of alpha over PQ, right? And so, oops, my entire graph is moving. Okay, so now we can see that the sine of this entire angle, right, which would be PB, right, this leg, divided by this hypotenuse, which is 1. Well, PB is just PR plus RB, and RB is the same thing as AQ. And OP is just 1. So we're left with PR, so that's cosine of alpha over PQ. So first of all, this thing is PR. So the divide by 1 doesn't matter, because anything divided by 1 is itself. So PR is, look, I'm putting this in here now. PR is cosine alpha divided by PQ, and AQ is sine alpha divided by OQ, right? Let's see here. Could have screwed something up. Just a sec. Let's see here. PQ is the sine of beta. Okay, got that. Oh, okay. That's right. Okay, I wrote this wrong, people. This is my fault. Sine of alpha is not, sorry, AQ. So sine of alpha, I should have written this out more explicitly. Sine of alpha is AQ over OQ. And so if I were to solve for AQ, this should be times OQ. Sine of alpha times OQ, and similarly, cosine of alpha times PQ. And so when you do this, these should have been time signs. So PR is, sorry for the confusion. I had times instead of, I had division instead of multiplication. OQ, sine of alpha OQ. So I've just substituted for PR, right? So using this, and for AQ using this. Okay, and then we also know that PQ and OQ are sine of beta and cosine of beta respectively. And so you would have cosine of alpha, PQ is sine of beta, sine of alpha, OQ is cosine beta. And so this is exactly what sine of alpha plus beta is. Sorry, my graph keeps moving. So sine, in summary, sine of alpha plus beta is cosine alpha, or in fact, usually what they do is they write this term first, sine of alpha times cosine beta plus cosine alpha times sine of beta. And so this is called the double angle property for sine. So if you have, say, sine of 70 or something, 70 degrees, and you don't know what sine of 70 is, but you do know what sine of 30 and 40 is, right? Then you could write this as sine of 30 plus 40, 30 plus 40, and using this property, you would say, so you know what sine of 30 is.
You can use 40?
Say you know it. I'm just saying, say you know it.
Okay.
Yeah. Then using this property, you would write this as sine of 30 degrees, cosine 40 degrees plus cosine 30 degrees, sine 40 degrees. So this is just one example of how you could use this computationally, but the real power of this lies in what you can do analytically. So again, in pre-calculus and calculus, this is a very helpful way to solve trigonometric equations. And you can do the same thing with your cosine double angle. So if you wanted to find what cosine of A plus B is, it's not much harder. Okay, so I'm going to have to erase some of this stuff. It's very messy. And I'll summarize everything at the end. Okay, well, it turns out, I don't know if it's worth, it's a very similar argument. My computer is also being very slow. Basically, you use the same trigonometric relations that we found here, and you would write some ratios. So OA to OQ, that's OA, that's this, to OQ, which is this, that's the cosine of alpha, and RQ to over PQ, well, that's the sine of alpha. And then, using these same using the same things that we found here, you would find that cosine A plus B, I'm not going to go through the details, it's very similar to what we just did. Cosine A plus B is the cosine of alpha times cosine beta minus sine alpha sine beta. So this is the cosine double angle property. So sorry, this was rushed. I want to make sure you all have enough time for your quiz. So anyway, so I showed this rigorously. I didn't show this rigorously. I just sort of hand waved my way through it. But I hope that this was clear to follow. Sorry about my mistake here. I had it divided by sine instead of a times sine. Okay, anyway, I will send the quiz now, which doesn't make you solve. I mean, you're not going to be doing anything super advanced, but there are some questions that involve radians. Okay, so I've just sent the quiz. So get started on that. There are some questions that involve radians, and so you need to know how to convert from degrees to radians to degrees and degrees to radians. And just to remind you how to do that, the conversion factor is 180 degrees in pi radians. So if you have something in radians, say you have x radians, then you would have to multiply by 180 divided by pi to give you that value in degrees. So I'll leave this up here for you to see.